Hello, welcome everyone. Good to see you. What a great crowd. This is awesome. Good afternoon. Thank you. Thank you so much. I'm Heather Antical, the Dean of the Faculty at CMC. I'm really excited to be here to honor one of Claremont McKenna College's distinguished teacher scholars, Branwen Williams, the George R. Roberts Professor of Integrated Sciences, Environmental Science. This endowed chair, originally titled the George R. Roberts Professor of Environmental Biology, was established in 1990 by CMC alumnus and trustee George Roberts and his family through the Roberts Foundation. George Roberts graduated from CMC in 1966 and is the parent of a 1993 CMC alumnus. He is the co-founder and co-executive chairman of the global investment firm KKR, which he founded in 1976 with his cousin Henry Kravis, a 1967 CMC graduate and also a significant CMC benefactor. Mr. Roberts has been a CMC trustee since 1982 and is a life member of the Roberts Environmental Center Board. Over the years, Mr. Roberts and his family have demonstrated exceptional generosity to CMC in support of student financial aid, public art, and campus facilities, including the Roberts Pavilion. They also established the Roberts Environmental Center, the George R. Roberts Faculty Leadership Initiative, which resulted in 27 faculty chairs, and most recently, the Roberts Integrated Sciences Center and Computational Matching Initiative, which is leveraging donor support to fund the Integrated Sciences strategy. In 2022, Mr. Roberts made a $140 million pledge to CMC to support the expansion of the full development of the eastern half of our campus, doubling the CMC footprint to over 150 acres and activating areas for new academic facilities and student housing, recreation and playing fields, and gathering spaces to encourage engagement and interactions. In his honor, CMC has named this expansion the Roberts Campus. At the 2014 Roberts Pavilion groundbreaking, Mr. Roberts said, "One of the best things that has happened in my life was I was rejected by a school in the East that started with a Y, and I got accepted at Claremont. So thank you, the East Coast school that starts with a Y, for paving the way for Mr. Roberts to attend CMC and subsequently open up so many doors of opportunity, including the chair position held here for the person we're here to celebrate, Professor Branwen Williams." In addition to holding the George R. Roberts Professor of Integrated Sciences Environmental Science Chair, Branwen is also the director of the Roberts Environmental Center. Her research seeks to understand the response of our environment to human activities. To do this, she develops and interprets records of environmental variability in our oceans, from the tropics to the poles. She also works with local communities to help build resilience to climate change. Sorry about that. Branwen received her Bachelor's of Science from the University of Guelph, Canada. Love Canada. I'm also Canadian, so us Canadians have to stick together. Her Master's of Science from the University of Quebec at Montreal, and her PhD from Ohio State University. She is a National Geographic explorer, and her research is funded by the National Science Foundation and the National Oceanic and Atmospheric Administration. Previously, Branwen served as the co-director of EnviroLab Asia, a 5C program funded by the Henry Luce Foundation that focused on using community engagement and multidisciplinary lens to understand environmental issues in East and Southeast Asia. In a moment, we will have the pleasure of listening to Branwen speak on Inhabiting Earth, Stories from a Climate Scientist. Branwen. Branwen. As the Dean of the Faculty at Claremont McKenna College, I'm pleased to present you with this special medallion in recognition of your position as the George R. Roberts Professor of Integrated Science, Environmental Science. Engraved with the college's seal on one side and your name of the endowed chair on the reverse. Uh-oh, my fingers are not doing the turning here. Sorry, everyone. The medallion is a symbol of the honor you hold and is worn with your academic regalia. Please join me in congratulating Branwen on this most wonderful achievement. Okay, I'll clean it up for you.
Thank you so much, Heather, Dean Antical, for that introduction, and thank you all for coming today. Thank you for Special Events with CMC for helping put together all the details with today's program, the ATH for hosting us, that delicious meal. I'm looking enviously as some of you are eating your desserts. Hopefully mine will still be there when I'm done. Thank you all for coming today. So many of you have been my faculty colleagues through the years, my Keck faculty, who most of the work that I'm going to talk about today was done when I was with you, but then also my CADIS faculty on this new journey that we're starting, building a new integrated sciences department, one of which, foci, is thinking about our Earth. Thank you to the students. I have some of the REC students that are here, some of my advisees, some of the students that do research with me or have been in my classes before, and really, we're all here for you all. And finally, at the head table, I have my family is here. My daughter is sick, so she wasn't able to join us, but I've been promised we can take a meal home for her. And my EnviroLab colleagues that are sitting up at the table with me, who we spent a lot of time learning about each other's disciplines outside of campus, which really helped me kind of go from being a natural scientist into really a liberal arts scholar. So today, I'm going to talk a little bit about my journey from being a student and learning about the impact humans have on our planet, to being an early career faculty member, really focusing in on climate change, to kind of where I am today and thinking about how do we deal this huge problem that is facing our society. I'm going to trace that journey a little bit over the time that we have for the rest of our lunch. I thought I would start with a picture of me in the field, because if we can't take fun photos of us in the field, and what's the point? And in this picture is from a couple of years ago. I'm actually in the Canadian Arctic, and I'm standing on top of about 400 meters of ocean water, standing on the sea ice. 400 meters would be about 4 skyscrapers kind of stacked on top of each other. It's July, so right after the longest day of the year. And if I'd come back a week or two later, I would have been swimming. It's a melt pool at the very bottom right. And what I want you to take away from my talk today is that our Earth is an amazing, dynamic, interconnected system, but the changes that humans are causing are dwarfing some of those natural processes that we understand that drive variability on our planet. Now, I did starting my undergrad career wanting to save the oceans, and so I thought I would start back to some of my early field work when I did get to go down in a submersible as a graduate student. This is the Johnson Sea Link. I think it's out of commission now, but I was able to go down and explore some deep sea coral reefs off our coast. These ones are from the Gulf of Alaska. This video was actually taken with a remotely operated vehicle. We didn't go down and explore these ones in person. But these corals are amazing things. They kind of grow like trees. They have a hard skeleton. And then the pink kind of peach living tissue layer on top of them has little cups on them that feed on particles in the water. And so they are eating on all the things that are floating by them in the water. When they eat those particles, they ingest it. And the chemistry of those particles incorporates into the chemistry of the skeleton. And like trees, these corals grow with a trunk at the bottom. So this is, you maybe see the growth rings in this coral section, and kind of like a tree trunk has growth rings in the tree. And like a tree, it's older at the inside and younger at the outside. And these corals lay down their skeleton in these bands year after year after year, incorporating the chemistry of what they're eating in those little particles into the chemistry of their skeleton. So one of the things that we do is we actually measure the changes in the chemistry across time in the coral to reconstruct changes in the chemistry and the properties of our oceans, which is intimately linked to what's happening in the atmosphere. Now, one of the things that really kind of stuck with me when I was a student was realizing the impact that people can have on our planet. And the first time that this happened, when I had this realization, was actually measuring a type of carbon, radiocarbon. Radiocarbon is radioactive. It's produced naturally in the atmosphere, and then it decays away naturally as well. It's always present in low concentrations, and there's no kind of significant health implications from it, even though it's radioactive. In the 1950s, human activities artificially increased the amount of radiocarbon in the atmosphere by a significant amount. Does anybody know what we did? We tested thermonuclear bombs, and this increased the amount of radiocarbon by 2 orders of magnitude, which means it went down from very low levels all the way up to almost 800 in the atmosphere. We call this the bomb curve, or the bomb spike, this significant amount of radiocarbon tracing humans' activities. This radiocarbon produced in the atmosphere then dissolves into the ocean, into the dissolved carbon that's in our ocean everywhere. It gets taken up through photosynthesis into or organic carbon. So all the plants, the small plants that live in the surface waters, some of those plants die and they sink, or they get eaten by animals. Those animals might poop and that will sink, or they might, eventually they'll die, they'll decompose into smaller particles as they sink down into the depths of the ocean, where they get eaten by these corals. And that radiocarbon gets incorporated into the skeleton of the coral, and we can measure that carbon in the radiocarbon through the coral skeleton over the period that humans have been altering carbon in the atmosphere. And so through this, I realized that humans' activities in the 50s and the 60s and the 70s had permeated our entire atmosphere of our planet, had dissolved into the ocean, got taken up into our primary productivity, into our organic matter, into life, sunk down to the deepest parts of the oceans, and been archived in these corals that can live for hundreds of years. Now again, radiocarbon, it doesn't have any health impacts. This is more a tool that we use now to trace carbon chemistry in the ocean, but we're doing other things with our carbon cycle. We're putting carbon dioxide into the atmosphere, and that is causing harm. So I use corals and marine organisms to understand our past world. Other scientists use other archives to trace our histories of our climate. Some of my colleagues go down to Antarctica and they take ice cores. These ice cores go deep into the ice sheet on the Antarctic continent, and they can actually measure changes in atmospheric carbon dioxide through time. Now, one of the cool things about being a climate scientist is we can actually time travel. So we're going to do a little bit of time traveling today. Here we're going from 800,000 years before present all the way until the recent past. And so I'm going to show you a lot of these time series graphs going from left to right. I'll always try and orient you because we are going to jump a little bit through time. And then the y-axis is our variable of interest. In this case, it's carbon dioxide. We can see that over that past almost million years, carbon dioxide has naturally fluctuated from about 180 parts per million up to about 300 parts per million. During when the atmospheric carbon dioxide is lower, we have our glacial periods, our ice ages. In these eras, this is when Greenland's already covered in ice, but the northern part of the North American continent is also covered in ice. Anybody from Boston, New York, Northeast, you would have been under about 2 or 3 miles of ice about 20,000 years ago during our last glacial maximum, when our carbon dioxide concentrations were low and our atmospheric temperatures were a lot colder. Of course, now we can think about what we're doing in the atmosphere. We're putting carbon dioxide. I still remember when I was teaching in the classroom and we passed 400 parts per million for the first time. This gives an example of how fast we're putting that carbon dioxide into the atmosphere relative to the natural processes that move it in and out of the atmosphere over the past million years. Now, 400 parts per million, that's actually a really small number. It's about 0.04%. But it turns out that some things in small quantities can actually be quite dangerous. For example, arsenic can cause harm at those concentrations. Now, carbon dioxide varies. With our interglacial glacial cycles, a lot of that is carbon moving in and out of the ocean. What we're doing now is taking carbon that's in our fossil fuel reservoir underneath our Earth, and we're putting it up into the atmosphere. And that's causing warming. There's correlation. As temperatures go up, so does our carbon dioxide goes up. It's a gray line. And here I'm mapping temperatures also going up, going from about 1850, which is when we first started measuring temperature of our planet, up until present. But we also have a causation. We know that the greenhouse gases create a blanket around our planet. that the sunlight can largely come through this blanket. Some of it's going to be reflected, and some of it is going to be absorbed. It changes character when it's absorbed, and a different kind of properties of energy is re-emitted by our planet back into space. That energy is captured by that blanket of greenhouse gases and prevents it from leaving, which keeps our planet warm. In fact, thank goodness for greenhouse gases, because if we didn't have them, our planet would actually be about minus 18 degrees Celsius, which is about 0 Fahrenheit. So we do want to have some greenhouse gases in our atmosphere, which makes our planet habitable. But what we're doing is we're increasing the thickness of that blanket by putting more carbon dioxide into the atmosphere. That is keeping the energy in our planet, and it's causing warming. So this is where I was when I kind of ended my graduate career, thinking about my graduate degree, thinking about the fact that I initially wanted to, think about the ocean, started off as a marine biologist, but the biggest pressing concern of our planet today is this warming that's happening. And so I started early career. I came down to the Claremont colleges in 2011, really thinking about a lot of this variability. What does this mean? How does our Earth system work? How is temperature connected to carbon? How are the oceans linked to the atmosphere? And I still work on these corals, but I started thinking about using other tools that are available to us as well. I no longer go down in submersibles, but I do go scuba diving. Often when we think about scuba diving, we think of warm, tropical, sunlit waters with sea turtles. Sometimes it is in Maine in the spring in a wetsuit, and it's only about 6 degrees Celsius. The reason I go is to collect these marine algae. Now you might be thinking, I don't see any algae. This is an algae skeleton. This species of algae forms a hard rock. We call them marine calcifiers. They calcify a skeleton. And they, similar to our ice cores and to our trees and our corals, they form the skeleton with growth rings through time. So we can measure the changes in the chemistry of these growth rings and the properties of the growth rings, how fast they grow from year to year. And we use it to understand changes in our environment. These algae can live a lot longer than any of us. The oldest one we have archived is about 660 years. We think that they're older, but turns out not a lot of us want to go diving off the coast of Labrador and northeastern Canada to where we think they have maximum lifespans. Now, I think about these shorter timescales, but in my community, we think across much longer timescales as well. So now we're going to look across 65 million years. So 65 is back here, all the way towards present. My kind of research is in this little bit, these squiggles in here. This is the last million years, and this is those interglacial glacial cycles that we thought about. We're looking at temperature now. 0 is what temperature has been over the past 100 years, and you can see that we go down about -4, -5 degrees Celsius, and then we go up to 16 to 20 degrees Celsius. And if people ever say to you, wow, the climate's been warmer than it has been today, yeah, they're right. It's been a lot warmer in the past than it has been today. We can go back about 50, 55 million years ago, and the climate was maybe 8, 10, 12 degrees warmer than it was today. And we call those hothouse climates. This is when carbon dioxide was maybe 3 or 4 times higher in the atmosphere than it is today. There was no ice on our planet. Sea level was about 100 meters higher than it is today, and our system was a fundamentally different world. We also didn't have people. So maybe that, our system is dynamic and it changes, but it really depends on the impacts of these changes on people and where we live. You can see that through time, the temperatures have come down through processes that we have a pretty good understanding of. Some of it is all of that rich life that lived on our planet when it was warmer. It died. It got buried. Through time, with increased temperatures and pressures, it started changing into some of the fossil fuels that we are now burning today. And some of it, through natural processes and chemical reactions, took the carbon out of the atmosphere and put it into the ocean. There's other important things that happened. You'll notice that there was a big drop in temperature about 35 million years ago. And this corresponds to when Antarctica went from being a transient ice sheet into a full ice sheet on East Antarctica. Ice is a really important role in our climate. It's really reflective. So when sunlight comes down and hits our planet, if it's hitting on ice, more of it's going to reflect and go back up into the atmosphere. As we melt ice and we reveal maybe water underneath it or a darker colored landscape, we actually will end up absorbing more of that energy. As you absorb energy, it gets warmer, which melts the ice, which means that more energy gets absorbed, which means it gets warmer, and you melt more ice. And you have these runaway processes that start to rapidly transition you from different stable states. So from a warm house climate into a cool house climate. Now, climate scientists don't only look into the past, we also get to time travel into the future. And we do this using our climate models. Here is an example of how we test our models. So we're going from 1850 into 2100. I'm not showing you the data for the future yet. And we're looking at difference in degrees Celsius from about 100 years ago. The black is our instrumental temperature, and the purple is an average of different model runs. So there's about 30 different global climate models around the world that are used for these comparisons. I always joke that the Canadians have one in British Columbia, the Americans have one in Colorado and New York, the Chinese have one, the Japanese have one, and all these different really top-tier research institutes will run their climate models using the same set of scenarios, and then they'll compare their results. And if we look at how we run these into the past, so we call these hindcast, we can see that the models actually agree pretty well. The dark purple is the model average, and then there's a little bit of disagreement among the models and the temperature that they kind of hindcast, but it encapsulates what our instrumental temperatures have been recording for us. What this suggests is that we can have confidence in our models when we use them to then project into the future when we don't have a way to test. Turns out waiting 100 years to see what happens is not a great strategy to figure out what to do about climate change. So this is what happens when we run our models into the future. There's 4 different pathways, and those pathways are not determined by the science. They're determined by what people decide to do. They're called the shared social economic pathways, and they're examples of how a society might progress. This purple one at the bottom is our sustainable future. This is what happens if people stop burning fossil fuels today. We can largely limit warming to 1.5, maybe 2 degrees Celsius, and we can avoid most of the implications of climate change. Conversely, this yellow one at the top is our intensive fossil fuel future. This is if we continued to have burned fossil fuels as we were a couple of decades ago. We've largely avoided this intensive fossil fuel future, but it gives us a baseline scenario as if we were to continue on the pathway of what we were doing. We are right now somewhere in this direction. So we can use our geological past to put that into context. We can think about our last glacial maximum, which was about 20,000 years ago, where we were pre-industrial, before we started warming our climate, where we are today. If we do that sustainable scenario, we end up today. If we do the middle of the road, we're actually warming our climate back up to where we were about 3 million years ago. And if we had done our high emission scenario, we're taking our planet back to where we were about 50 million years ago. Now, the previous graph I showed you, the world ended at 2100. It turns out it doesn't. This is what happens when we continue running our projections forward into hundreds and thousands of years. Right now, we're committed to about 3 degrees of warming, which puts us right here. Greenland ice sheet is at risk. It is likely to melt if we continue on the trajectory we're on. Greenland ice sheet melting will put sea level rise about 7 meters higher than it is today, which impacts about 10% of the world's population who lives in coastal areas that are low-lying. If we continued on our intensive fuel, high emissions scenario, then we're melting West Antarctica. If we can keep our fossil fuel emissions down and bring us down here, then Greenland is likely to persist, and we will have avoided much of the dramatic consequences of climate change. And again, how are we doing? Right now, we are somewhere between the middle road and the high emissions. We've committed, based on all implemented policies, to 3.2 degrees Celsius of warming. Now, this is when people look at me and they're not very impressed. Some of you suffer from the climate blues. And I have to say that when I was kind of ending my early career, this is how I felt too. We had missed the opportunity to stop climate change. It is happening, and now we need to think about what we're going to do going forwards. But I'm also really, really optimistic, and there's a couple reasons why. First of all, this is a quote that brings me a lot of inspiration. It's from John F. Kennedy in 1962. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard, because that goal will serve to organize and measure the best of our energies and skills, because that challenge is one that we are willing to accept, one that we are unwilling to postpone, and one in which we intend to win. People have done hard things in the past before, and we can do it again. The thing with climate change is it's a people-caused issue, and people can solve it. I used to joke in one of my classes about how it's not like an asteroid is going to hit Earth, right? That killed off the dinosaurs. Turns out, last year, NASA sent up a missile into space and deflected the pathway of an asteroid. It wasn't going to hit Earth, but it was their first test of the planetary defense system, which means we can now avoid asteroids from hitting Earth and causing mass extinctions. If we can do that, if we have a planetary defense system to stop asteroids from hitting the Earth that killed the dinosaurs, we can also solve climate change. The other thing I'll point out that I think is really important is that we don't need to do it at the cost of people. This is a figure going from 1890 towards present, and I'm plotting the GDP per capita versus CO2 per capita, and this is for the United States. What you'll see is that for about 80 years, they changed in lockstep. If we wanted to increase the GDP, if we wanted to increase our quality of life, we did it by burning fossil fuels. But for a long time now, since about the 1980s, those have been disconnected. We can continue our quality of life and not have to do it at the cost of fossil fuels. Now, of course, we need to get off fossil fuels, so we need to bring it all the way down there. But I can also say that my fossil fuel, my carbon dioxide per capita consumption is less than my parents', and maybe even less than my grandparents'. So we have been making strides. We have avoided that high emissions scenario. So going forward, what do we need to do? Well, we need to mitigate. We need to reduce greenhouse gas emissions to minimize the temperature rise. We are committed to a temperature rise. We're probably at 1.5, maybe a little bit above that. But if we can start decarbonization immediately, we can stop it from getting much worse than that. The strategies for decarbonization, I like to think of it as our reduce, replace, and remove. The removing, this part, is right now a bit of a wild west. This is when we're taking carbon dioxide in the atmosphere and taking it out. There are some technologies being proposed. Some of them might work. Some of them might not. Probably a lot of them won't. I don't want to be reliant on technologies that are not yet existing. So let's think about how do we reduce and how do we replace. Reducing our energy is not very glamorous. It's in the building mechanisms of how everything works, but it needs to be done. Replacing, we can think about electrification for low and medium temperature processes. Much of our carbon is transportation. So how do we get off of fossil fuels for our transportation into zero carbon energy sources? I'm not going to say clean energy, because really no energy is clean. They all have trade-offs. But right now, we need to get off the ones that are focused on carbon. And then we need to think about, for our industrial processes, that hydrogen might be the solution for that. And you'll notice that the DOE has recently talked about putting in 7 hydrogen hubs around the US. One of the reasons that I'm optimistic that we're making progress now is because people are putting their money into it. The latest bill, the Inflation Reduction Act, put in a couple of hundred of billions of dollars towards trying to address climate change. For perspective, with the Apollo program that took us to the moon, that cost I wrote this down to make sure I got it right, $25.8 billion between 1960 and 1973. With inflation, that was about $250 billion. So we're in the same scale of trying to solve climate change as when we went to the moon. But as I said, even if we mitigate, even if we get down to a decarbonized world fairly quickly, we've already committed to some warming. So we also need to adapt. We need to enhance the resilience and reduce vulnerability to climate impacts. The thing about climate change is it is an environmental injustice issue at the core. The people who are burning the carbon are not the people that are most impacted. So we need to bolster the resilience of those communities. Climate change is felt locally, and so thinking about Southern California, thinking about us, how do we build our resilience? The resource that I point people to is CalAdapt. It's put out by the government, some of the research institutions, and you can look at how climate change is going to impact your zip code. So you can put Claremont in there, and you can see that historically, we've had about 10 days that were about 99 degrees Fahrenheit or higher. In the future, we're probably going to have about 30 or 40 days that are 99 degrees warmer, 99 degrees Fahrenheit or higher than that. And students, those days will all happen in September, right when you come back to campus. So in addition to temperature, we also need to think about precipitation. On average, Southern California is going to stay about the same in terms of our water availability. It's within the noise of the model projections, but it's going to be a lot hotter, which means there's going to be more evaporation, and it's going to get a lot drier. And those droughts are going to be punctuated by more extreme flood events. So while average precipitation, average water might stay the same, we're going to swing from these really long, dry droughts to very sharp, intense storms. These storms are our atmospheric rivers. I don't know if anybody's watching the weather forecast right now. We're about 50%. One's going to come in later this week. I don't think it's going to be that dramatic, but we're keeping an eye on that. And a lot of what's happening with our weather in Southern California is dependent on what's happening in the Pacific Ocean. We also have an El Nino event that is still building in momentum right now. See, I get excited about these things. But what I wanted to do is bring this home right now and think about mitigation and adaptation. Some of this needs to be done locally. We all need to reduce our carbon. We all need to think about how climate change is going to impact us. But really what we need to do is we need implementation. We need to make sure that things happen. This implementation is action. It has to be economically feasible, and it has to be socially just, and it needs to draw from diverse stakeholders and experiences. And so when I think about climate solutions, and I am going to talk about it in terms of solutions, because even though climate change is happening, we can try and reduce what's the impacts of it, and we can bolster the communities that are going to be impacted the most. We need everybody, and we need people that are coming in from different experiences and different trainings and different backgrounds. And I'm just going to talk a couple examples on campus of how we're doing this. For example, if we think about some of our educators and our scientists and our leaders, we might think about what CMC is doing with their goals to reach carbon neutrality by 2040. This is a plan that is in place. They worked with a firm last year, and they have a pathway to reduce, replace, and then offset what's left over. So the CMC can be a leader in getting to carbon neutrality in coming decades. We might think about working with our communities. How does the policymakers and citizens and community members play a role? My climate change class for 2 years in a row partnered with the Conservancy at Pitzer and then with different communities. This example is the city of Adelanto. They're in the desert next to Victorville. It's already very hot and dry right there. My students worked with the community to identify how climate change is going to impact them specifically, and then strategies they could start working towards to try and build resilience towards those impacts. The REC has been leading in this for a decade under the leadership of Bill Asher and Kristen Miller. One of their team projects last year was working with a high school in Pomona to look at how to mitigate the heat island effect. Urban heat island is when you have more buildings and less trees, you can cause localized warming. How can you offset that for the locations that our children are playing outside? We can also think about educators and storytellers and really thinking about cross disciplines. And the REC is working with the Nature Conservancy on environmental education programs, both to educate us when we get to spend time in nature and see the way that nature is dynamic and interconnected and how we play a role in that, but also to build education curriculum for younger kids, particularly in areas that don't have the ability to go out and explore nature on their own, so that we can build stewards for our environment going forwards. And then my last one is a brand new one that we've just started. I'm really excited about it because it's a collaboration of the sciences and the humanities. We're working with a glaciologist, myself, and a high school teacher, and then we have 2 REC interns. And we're building a curriculum for a high school where we're going to educate students on climate science so that they can write climate fiction stories in their English class of how society might live under future climate scenarios. We need everybody to be involved, whatever your training is or your interests and your backgrounds. So if we think about how do we deal with climate change, what I want you to take from today is that we have to mitigate. We have to reduce our carbon emissions. We have to replace them into low carbon or zero carbon solutions. And we need to remove what's left over to keep our planet away from those tipping points, like the ice feedbacks. We have to adapt. We have to cool our climate. We have to cool our campus. We have to retain our water when it comes. But most importantly, what I want you to get from this is that we have to act. That solution for you is going to be specific to you. Where are your levers? How can you reduce your footprint? How can you build your resiliency to temperatures and water insecurities? And what can you do to help get other people to act as well? Thinking about reducing, biking more, driving less, eating lower in the food chain, getting people to vote, collaborating to share stories, talk with people when they have the climate blues to get more motivation from society. We all need to be working towards this, and I have confidence that we will, and that's why I'm optimistic. Thank you.
Thank you so much. That was so educational, and I felt like you broke it down where, for the first time, I feel hopeful about climate. Does anyone have any questions?
Branwen, thanks so much. It's fascinating. Could you talk a little bit about where you see both CMC, the Robert J. Center, and the 5 colleges developing in this area? It's such an exciting area.
Yeah, so one of the pillars of the new Kravitz Department of Integrated Sciences is our Earth. And I think it's taking a really forward-looking perspective, because it's not just to train more scientists. I feel like I've trained my scientists who've gone on to grad school, but really what we want to do is embed climate literacy throughout all of our students, so that all our students who are going into other careers as well, thinking about going into government or into industry or going into whatever our pathways our students follow, will be able to keep this kind of in the back of their mind and shift society, shift our actions to really cause change everywhere throughout society. And I think that the department, with a focus on our non-science majors as well as our science majors, is a really innovative and important way to do that.
Any other questions?
Thanks for this so much. The analogy to the race to the moon in the U.S., the numbers made sense, but that was the U.S. doing it for the U.S. to reach the moon. Now this is the U.S. dollars, but a world global issue. How do you reconcile that? Obviously their comment before is right. Those that didn't put the pollution in are going to deal with it in unfair ways, but tell me a bit about thinking there.
Yeah, I could have included about 20,000 more plots, but I don't think any of you would have appreciated that. But one of the ones you look at is per capita carbon emissions around the world. And the US, Australians, Canadians, actually have really high per capita emissions. And so this is a problem that largely we've created because of the development that we had as a country. And so it might be that in the future, other countries as a country might have higher emissions, but per capita, the US is still one of the top ones. And one of the ways I think about it is, if you think about Claremont and you think about Los Angeles, should Claremont and Los Angeles be able to burn the same amount of carbon? Well, no, because Los Angeles has X amount more people than Claremont does. Really thinking about per capita is the way to think about it. And so we need to reduce our per capita emissions even more so than we have done, and then allow other countries to increase their standard of living to where we are. And so I think it is a moral kind of requirement for us to let that happen. I also think that we can lead in new technologies, and there's a lot of opportunity for the US to become leaders in thinking about ways that we can decarbonize, and then sharing those innovations around the world as well.
Thank you so much. We have time for one more question.
I saw you are leading the upcoming Antarctica trip, which sounds amazing and fantastic. Could you share if you will be including any of your environmental values or lessons within the trip? Like, could you give us a little sneak peek?
Wow, so that will be in January 2025, which is pretty far away, so I haven't thought too much for it. I did get a chance this past summer to serve as a visiting scientist on one of the Lindblad National Geographic research vessels. We were looking for my algae in coastal Greenland to try and understand relationships between the ice sheet dynamics and then what's happening in the coastal oceans offshore. And I was very impressed with the way that these expeditions are trying to also educate. We, as a visiting scientist, it was a new program that they've run this summer, were able to speak with a lot of the guests on the ship. And we carefully steered around the topic of the carbon footprint of getting to these locations. The ships argue that they're carbon neutral. I think it'd be an interesting project to dig into that a little bit. But I think that there's a lot to be said for education and sharing what we're doing and understanding of our planet, and that there's a lot of kind of implications of that of people's actions later on. So with this trip, I want to focus a lot on just the natural beauty of our Earth, but also how humans are changing that and you know, taking it away a little bit. And so I am optimistic, but I think we also need to be realists as well about it. I haven't been down to Antarctica before. I've been up into the Arctic quite a few times for my research. And so it'll be exciting to kind of see a different part of our planet. A lot of my colleagues have gone down to the ice, and so it'll be fun with the CMC community to be able to explore such a remote location, but one that is not separate from our activities. Our carbon dioxide is reaching down to Antarctica as well. Their plastics are down there and pollution as well. So I think it'll be really interesting to think about nature, but also how humans and the far reach of our impact.